Hello everyone. On this video we will be looking at the area of a plane region. Okay, so to start we're going to begin with a formula that you should be pretty familiar with, and that's the area of a rectangle. Okay, and that area of a rectangle is equal to length times width. Okay, and now that one formula is going to be the backbone of everything we do in this particular video. Okay, because that shows us the area of a rectangle. But what if we wanted to know the area underneath a function? About the area of a non-rectangular function. Okay, so we know functions can have all sorts of crazy shapes and everything else. Okay, so what if we just took a portion, a small chunk of that odd-shaped function? Okay, so what if this is just a function f of x? Okay, so this is your function f of x. Okay, it may not be the whole function, but just a small portion of it. Okay, so let's say out of some odd-shaped function, we just decided to cut off a section between x equals some number a and x equals some number b. Okay, so that's the portion of the function. All right, so what if we wanted to approximate the area up under here? Okay, well, there's no formula that we can use to just get the area up under there. So instead of getting the exact area, let's get an approximate area. Okay, so what if we put one big old rectangle right up under there? So one rectangle. Okay, well, we may not have the exact area, but we know if we can figure out the length times width, we can figure out the area. So the only thing is we're kind of missing that portion and that shaded portion here. So we have an approximate area, it's just not very good. Okay, so we figure out the length and the width. This is our approximate area of under f of x. Okay, again, not a very precise approximation, but it is an approximation nonetheless. Okay. Now, what if instead of one rectangle, we have two rectangles? Okay, so again, we redraw that same function, and we get it there. Okay, and again, this is just our function f of x. And it's between some x equals a and another, let's say x equals b. Okay, so if we have two rectangles, let's say if we have one rectangle from here to here and another rectangle from here to here. Let me kind of straighten that dotted line up. Okay, so we have our function, and we now have our area of rectangle number 1 and rectangle number 2. Okay, so what does that tell us? Well, we know that figuring out the area, we're missing out on the little sections there. Now, it's not as big as the sections here. Believe it or not, we're actually a little bit better because we have more of the area underneath covered. Okay, this little section here and this little section here is not as bad as that entire missing section up there. Okay, so if we add rectangle number 1 plus rectangle number 2, we get another approximate area. Okay, just a little bit better. So this one's a little better approximation. Okay, again, not perfect, but a little better than just one measly triangle. All right, so if using triangle, why do I keep saying that? If using one rectangle was okay, and using 2 rectangles was a little bit better, what if we decide to use 5 rectangles? Okay, so we have our function here. And again, this is our f of x. So if we go between some x equals a and x equals b, let's say we have rectangle number 1, rectangle number 2, rectangle number 3, and rectangle number 4, and rectangle number 5. Okay, so we'll call this rectangle 1, rectangle 2, rectangle 3, rectangle 4, and rectangle 5. So if we want to get another approximate area, we just add the area of those 5 rectangles. Rectangle 3 plus rectangle 4 plus rectangle 5 will again give us an approximate area, where now we're just missing a little bit less. Okay, we didn't account for those yet because we're using rectangles, so we're missing those sections. But if you notice, the sections we're missing out on is smaller than 1 rectangle and is smaller than 2 rectangles. So now if you notice, the more rectangles we add, we're getting closer and closer to an actual approximation up under here, because the amount that we're missing is getting smaller and smaller. Okay, so if we did a little bit better with 5 rectangles, think about this. The accuracy would increase if you had 25 rectangles. Okay, so if you had 25 rectangles under here and added them all together, you'd be okay. You'd really be able to have a pretty good idea of what the area is under here. But what if you had 1,000 rectangles up under here? Oh, you'd have very little space not accounted for. It'd be even better. But what if you had 1,000,000 rectangles up under there? Now, if you had 1,000,000 rectangles up under there, you would have very little noticeable shaded space that wasn't counted for. So if you had 1,000,000 rectangles, you can actually say that you have a pretty good idea of what the area would be up underneath your function. All right. Now, we're going to have 2 different types of approximations. So if you notice here, all of the rectangles are underneath our graph. Okay, so for this particular graph, you notice this function is decreasing. Okay, now because all of our rectangles are underneath the function, we have a specific name for those. So rectangles under the function are called inscribed rectangles. Okay, and those are actually useful when you're looking for your lower sum. Okay, so you want to remember that. It'll come in very handy on our examples. All right, so what does that tell us? Well, one thing we can figure out is, let's say if we have our XY axis here, and let's say we have, just like the ones above, we have a decreasing function. Okay, so this is your f of x, and it's decreasing. Okay, so if it's decreasing, and you have your x equals a, I'll put the a up under here, and x equals b, I'll put the b up under there. And if we have our inscribed rectangles, then you see for all of your inscribed rectangles, when the function is decreasing, the right endpoints are actually the ones touching the function. So your right endpoints touch the function. All right, so that's for a decreasing graph. What if it's increasing? Well, if you look closely and you have an increasing function, okay, and this is again your function f of x, and it's increasing. I'll put the increasing a little lower. You have an increasing function for some interval from a to b. Then in order to have inscribed rectangles, you can't have the right one touching. So you notice your left endpoint would have to be touching the graph. Okay, so if you notice here, all of your left endpoints are touching the graph. Okay, so that's the difference that you will notice when you have inscribed rectangles. And it will come in very handy when we start doing the examples. You'll see why this is important. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next page. Kind of straighten up my papers here. There we go. Now, we saw when the rectangles are underneath the function, but what if the rectangles are over the functions? Okay. Now, if your rectangles are over the functions, you'll have a little bit of a different problem. You'll still be able to approximate, but it'll be a slight difference in what you get. Okay, so what if we have our very similar function that we did on the first page? All right, so let's say if we have, this is our f of x. Okay, and this is between some x equals a and x equals b. Actually, let me move this f of x over a little bit because we're going to need that room. So this is our f of x here. Okay, so instead of a rectangle going underneath it, one big one, let's say if we had one that decided to go over the function. So let's say if we have one rectangle here. Okay, so remember this is our one rectangle. So what we're going to do is instead of going up underneath, we're now going to put one big rectangle over it to find out the area of that entire thing. Okay. Now the only difference is we're looking for just the area under here, which means all of this is just a bunch of extra. Okay, we kind of overshot that one. Okay. But we still have an approximation. It's not a good one, again, but we have an approximation. So we can see here that this is the approximation or approximate area of our f of x. Okay. Again, when you use one big rectangle, it's not going to be a very good one. But what if you use two rectangles? Okay, so again, we have our function, and let's say it looks something like that. And this is your f of x. And between the values of x equals a and x equals b. Okay. Now, if we want to use two rectangles, but we're not going to use inscribed rectangles, let's say if you want to go from here to here, it's one rectangle, and from here to here. Okay, so remember, this whole thing is, we're just looking for the area up underneath here, which means this, all of this dotted area, we kind of, again, we overshot it. We made our area a little bit bigger. Because remember, this is rectangle number 1 and rectangle number 2. Okay. Now, if you notice, this one big area here is not as, this one isn't as bad. Again, you still have way too much of a guess. Our guess is way too big, but it's not as bad as this one. Okay, so instead of stopping here and having all of that, you have like a smaller section up here. Okay, so again, this is a little better, not much. Especially if you just add rectangle 1 plus rectangle 2, which would give you your approximate area. Okay, so we, again, just a little bit better. It's not going to be much better when you're just using two rectangles, but it's a little bit better than we had with one. Okay, so again, just like before, what if we now use 5 rectangles? All right, so let's get our graph here. And again, this is our f of x. And this is between some x equals a and x equals b. Okay, so now we're not going to use inscribed. So let's say we have one rectangle, two rectangles, 3 rectangles, 4 rectangles, and 5 rectangles. Okay, and remember, once again, we're just trying to find the area up underneath the function. So this is all just extra guessing. Okay, we kind of overshot it again. So once again, our approximate area is if we add our first rectangle, second rectangle, third rectangle, fourth rectangle, and fifth rectangle. Okay, so once again, we're just adding all of our rectangles together to give it a really good guess. So your R1, R2, R3, R4, and rectangle number 5. So as you can see here, even though we estimated a little too much, when we went to 2 rectangles, it got a little bit better. Then when we went to 5 rectangles, the amount that we estimated too much for was just a little bit better. Okay, still too much, but it's just a little better. So as the number of rectangles increase, our accuracy increases. Okay, so just like before, what if we had 1,000, 25,000, 100,000, 1 million rectangles here? Even if we went over a little bit with each one, the amount we go over will get smaller and smaller and smaller. And that's what you want. You want your error to be just a little bit. You want it to be so small that it really means nothing. Okay. Now, just like before, I want you to notice here that these graphs are decreasing. Okay, each one of these, I drew them as decreasing. Now, if you notice on the decreasing graphs, actually this one I messed up a little bit on, because this should have been right here. My mistake there. There we go. All right, so if you notice, all of the left endpoints are actually touching your graph. Okay, so over here, notice your left endpoint, left endpoint, left endpoint are all touching the function. Okay, but they're all going over. Okay, so again, the estimated for this area is more than what the actual area would be. But when you have rectangles over the function, they are called circumscribed rectangles. Which we will use to figure out the upper sum. Okay, because remember, the inscribed rectangles, we left space that we didn't count when we tried to figure out the area. For circumscribed rectangles, we're counting too much space. We're going over the function. Okay, so that's why that's called the upper sum. Okay, because it's our big guess, where the inscribed rectangles is our lower guess, or lower estimate. I don't want to say guess, say our lower estimate. Okay, so once again, we look at a decreasing function for our circumscribed rectangles. Okay, again, we have our, let's say, a decreasing function. Okay, and that is between our x equals a and x equals b. Our rectangles all have one thing in common. our left endpoints are touching the graph. Okay, so for a decreasing function, and using circumscribed rectangles or upper sum, the left endpoints touch the function. Okay, now if we look at an increasing function, okay, so what if we have a function that's increasing, and this is our f of x between x equals a and x equals b. Again, this is our increasing function. If we wanted to have a circumscribed rectangle, we see here that the only way to do that is to go over the graph, but then all of our right endpoints. Oh, this one actually should have stopped there. Notice all of your right endpoints touch the function. All right, so once again, we know that our inscribed gives us a lower estimate because we miss a whole lot, but our circumscribed gives us too large of an estimate because we overshoot it with our rectangles. Okay, so now what we're going to do is we're going to look at how to find kind of a middle ground between the two. All right, so if you are still writing, feel free to press pause, but we are going to go ahead and move on to our next page. Okay, so to find the area, let f of x represent the following function. Represent the following function. All right, so let's say if we have some really odd looking function that looks something like that. Okay, so this is your f of x. All right, so let's say we just want to worry about a portion of the function between x equals a and x equals b. So we want to know the area up under there. Okay. Now, if we want to use an inscribed function, we're going to have to pick a point. So let's say if we have some point right here. Okay. Let's say we just pick that little bit of chunk out of the graph. Okay, we could have picked anywhere, but we just picked that chunk out of the graph. Now, the width of our rectangle chunk out of that graph, we're going to call that delta x, or change in x. Okay, now, this portion, since it's decreasing and touching the right side of the graph, we know that's inscribed. So this is our inscribed rectangle. So we'll call that height. Remember, we're just going from here to that inscribed rectangle, f of m sub I. Okay, because remember, your f of x is whatever point on the graph. Okay, so that's f of m sub I. But let's say we also wanted to find our circumscribed rectangle, the height of our circumscribed rectangle. So let's say if we wanted to find this rectangle. Okay, because remember our inscribed is just this rectangle right here. Go ahead and darken that up. Our circumscribed, remember, since this is decreasing on this interval, our left endpoint is going to touch the graph. So the height at that particular point is going to be f of, let's say we use capital M sub I. Okay, so just to make sure, we know that our delta x, that's called delta x, and that's the width of the rectangle. Okay, just how wide the rectangle is. Okay, so our f of lowercase m sub I, that's the height of our inscribed rectangle. Remember, our inscribed rectangle is decreasing, so our right endpoint touches it. So height of inscribed rectangle and our f of uppercase M sub I is the height of our circumscribed rectangle. Uh-oh. All right, now, one thing we know for sure. We know that the area of our inscribed rectangle, remember it's underneath, area of inscribed rectangle is actually less than or equal to the area of our circumscribed. Because remember, our circumscribed, we overshoot our estimate. We make a bigger rectangle that goes over the graph. And our inscribed, we make a smaller rectangle that's underneath the graph. Okay, so that means our f of m sub I times delta x, which is our inscribed rectangle times the width, so width times height, is less than or equal to the height of our circumscribed rectangle times the width. Okay, so the one thing we can figure out with this is that, well, not one thing, but another thing we can figure out with this is the fact that our inscribed rectangle and our circumscribed rectangle, okay, so you have too big of an estimate and too small of an estimate. Somewhere in between our actual area exists. Okay, so if we guess too low and we guess too high, somewhere in the middle would be our actual area. Okay, so what if we let n equal the number of rectangles as n approaches infinity? The area will get closer and closer until the limit of your inscribed rectangle will approximately equal the limit of your circumscribed rectangle as n approaches infinity. All right, so if we wanted to give this kind of a visual, let's say if we have our function, just a quick little visual, and you have your inscribed rectangles, and you have your circumscribed rectangles. Okay, remember that goes over the function. Okay, so here, remember, we guessed too small, we miss out on that. We guessed too big, so we have too much of a guess here. Somewhere in the middle, we're going to have the actual area that is perfect. That's the perfect estimate underneath that function. Oops. That up. There we go. All right. So now we're going to take all of that and give a nice definition for it. So if you are still writing, feel free to press pause. We're going to go ahead and move on to our next page, which is the definition of the area of a region in the plane. All right, so what if we let f of x be continuous and non-negative on the interval x equals a to x equals b. The area is bounded by the graph of f of x the x-axis, and the vertical lines x equals a and x equals b. Okay, so to give you kind of a quick little visual, again, let's say if we have our graph, it looks something like that. Okay, so it's continuous, our function is continuous, and it's bounded by the graph of f of x, so this f of x, the x-axis, so this is your x-axis, so bounded above here and below here, and the vertical lines x equals a, so this may be our x equals a, and this will be our x equals b. So the area up under here is what we're looking for. Okay, so to find that area, that's going to equal the limit of f of some c sub I delta x. Okay, so what if we pick one little section that's not below or above? Well, let's say it's right in the middle. Okay, where you have the same amount below and above. So let's say this is our C sub I. Okay, so with these, let's say this left side is our X sub I minus 1. Let me clean that up a little bit. So you have X sub I minus 1, and the right side is your X sub I. So that C sub I is between those two values. So that's where X sub I minus 1 is less than or equal to C sub I is less than or equal to X sub I. And we know our delta X is equal to B minus A over N, where N is equal to the number of rectangles. All right, so we were able to, just from that long drawn out group of examples before, figure out this definition. All right, so now we can use that to come up with a general definition. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move this to the next page instead of trying to squeeze it on this one. Okay, so in general, we're going to let f of x be defined on the interval from x equals a to x equals b, and we're going to let our delta be a partition of the interval from a to b, given that our a, which is equal to our x sub 0, so that's going to be our first point, it's going to be less than x sub 1, less than x sub 2, less than a whole bunch of other points, which is less than x sub n minus 1, which is less than x sub n, where our x sub n is equal to our b. And delta x sub I is the width of the ith subinterval. Is the width of the ith subinterval. Okay. Now, if our point C, or C sub I, is any point between x sub I and x sub I minus 1, then the sum, and that sum is the sum from I equals 1 to n, f of C sub I delta x sub I, given that x sub I minus 1 is less than or equal to C sub I, which is less than or equal to x sub I, is called the Riemann sum. Alright, so this video was mainly used for the explanation and definition, things like that. So the next video will have all of your examples and things like that. So hopefully this video made sense, and I will see you on the next video.